Greetings and welcome, friends. Today we're talking about solving absolute value inequalities. It's like our concepts of inequalities and our concepts of absolute value have combined their powers to be Captain Planet. Almost like that. But first, let's talk about some more extensions on the concept of inequalities. I want to talk about compound inequalities. So I've got a couple little definitions here for you to consider. A compound inequality containing and, all right, notice the italicized nature of this word and, all right, is true if and only if both parts of it are true. Okay, all right, we'll explain what that means in a little bit. An intersection is when you have the graph of a compound inequality containing and, is the intersection of the graphs of the two inequalities. All right, so we'll see what that means later. That'll be interesting. And a union, all right, happens when you have a compound inequality containing the word or. So there's and, right, and then there's or, all right, and it is the union of the graphs of the two intersections. All right, so if I have, for instance, an or problem, saying it's like greater than this point or greater than or equal to this point, the union would not be the individual graphs, but it would be the entire combination of the graphs, right? And if I have a compound inequality, all right, with an intersection, say I said, oh, it's got to be greater than or equal to this point, and, my bad, and less than or equal to this point. So if I have like an and sort of relationship, the actual solution would be the intersection of these two graphs, all right, where they coexist. All right, so if I brought these graphs together, notice a point here is true for the second graph, but not for the first, and the word and would not be describing that situation. So it's got to be true for both this and this in order to be on my final graph. So the intersection would look something like this, where I just have that, and everything shaded in between. All right, so that's a quick basic analysis concept of that. But let's talk about solving some compound inequalities, what these might look like. So here's a compound inequality. Notice this one is actually an and problem because, and you don't have to write this down, I could have written this as 5 is less than 2x minus 1 and 2x minus 1 is less than 11. So I could have perceived it as that if I wanted to. All right, but instead we seem to have this all written in one continuous line, and notice the existence of the double less than signs, double inequalities, okay, is what we've got going on. So instead of two sides of an equation or inequality, I've got like three sides almost, is what's happening. So this is a compound inequality with a and going on. It's not, you're only seeing this, but it's and because it's both things are true at the same time. Two relationships simultaneously there. So pretending, imagine this 5 is less than part wasn't here. If that wasn't there, how would you solve this for x?
I would add 1 and divide by 2.
Exactly, right? We'd add 1 and then divide by 2. So if I have 5 is less than, and I'm just going to rewrite this real quick, 2x minus 1 is less than 11. First thing I would do is add 1 to both sides. However, wait a minute.
There's 3 sides.
There's 3 sides, so what do you think we'll do?
1.
Add 1 to all 3 sides, right? And it's perfectly legal to do that. Okay? And now, what do you think we would do?
Divide by 2.
Divide by 2 on all 3 sides. Now, question, do I have to flip these inequalities?
No, because you're not writing
Correct. So if I multiply or divide by a negative, I would just double flip both of those guys, right? Flip them both sort of thing is what we'd end up getting. So I get 3 is less than x is less than 6. This is the solution to our little compound inequality. And if I wanted to graph that, here's 0, here's like 3 or something, and here's 6. All right, so if I want to graph this, I could graph this as the intersection of both of these things. So if 3 is less than x, that's the same as saying x is greater than 3, right? From x's perspective, it's bigger than 3. So that would be an open circle at 3, everything shaded to the right. However, this is an and problem, so I'm only going to graph the points that are true for both of them. Okay, so you could think of it, it's shading some way in this direction, right, over there. And for x is less than 6, that would be an open circle at 6, and shaded less would be to the left. And even though that's technically true all the way down to negative infinity, I'm only graphing the points that are true for both of those relationships simultaneously. So the ones that are true for both of them would be all of the points in between both of those values. All right, so that's called an and problem when it's compounded and you've got shading in between 2 points. All right, we've got 2 boundaries that we're looking at essentially, 2 constraints. So let's look at one more problem like that. Example A, another compounder. Here we are. And this one's logically a little bit different. This one's got an or thrown smack dab in the middle of it. So with that or, that means I'm going to, wait a minute, that says x4? Huh. I think that was supposed to be x over 4. That's not cool. That's not cool. Guys. Yeah. Yeah, I'm fixing that right now. I'm recording, don't you worry.
It wasn't working.
Here. Don't you worry.
Will I get a detention if I blow my nose during a video?
No.
Emily, he said yeah.
You said no.
Uh-oh. Nah, that's fine, don't worry. So, here we are. I don't know why it lost my fraction there. But, so this is what we got. Right. So what I'm going to do, this or thing, the solutions are going to be the ones that are true for either this. If it's true for this, it's a solution. If it's true for that, it's a solution. If it's true for both,
It's not a solution.
well, if it's true for both, chances are it's not going to be true for both. But all it needs to be true for is one of them in order for it to work. All right. So let's solve just each of these separately. So over on this side, I would just plus 1 both sides. So I'd have 3x is less than 6, and then divide by 3. And I'd have x is less than 2. Aha. Over here, we'd subtract 3 from both sides, right? And I'll have x over 4 is greater than, 2. And how do I get rid of the over 4?
Multiply by 4 over x.
Well, actually just multiply by 4. I want to keep the x there,
Yeah.
so I actually am fine with that staying. So I'll get x is greater than 8. And this or here logically has been true all the way down, so I could throw a little or right there. And this would be my compound inequality with an or
Boom.
logically taking place there. So if I wanted to graph this, let's see, 0 would be like here, this would be like 2, 8 would probably be around here-ish, right? So I'm going to have x is less than 2 as an open circle at 2 shaded to the left. All right, and x is greater than 8 would be an open circle shaded to the right. And even though 0 is only true for one of these, it's still a solution, right? Even though 10 would be a solution for only the one on the right, it's still a solution of the entire statement because of the operative word or there. It allows only one of those needing to be true at a given point. All right, so that's not too crazy, I don't think, right? It's not too bad. So how's this going to help us? Well, I'll tell you what. It turns out this concept is going to be helpful when solving, you guessed it, absolute value inequalities.
Oh my goodness.
Oh man, mind blown. So, check this out. Let's see, I've got the absolute value of the quantity x plus 1. It's all less than 7. All right. So, here we go. First thing we do, let's deal with the absolute value. It's already isolated, so normally what we did back in the day was we'd break it up. Same process, same procedure. So I'm going to have either x plus 1 is less than 7.
And then is it going to be x plus 1 is greater than 7 or less than -7?
We'll have to think about that. Now, the inside of this, the opposite could have been true, right? This could have equaled -7, right? So I'm going to say, or sorry, been less than -7 or whatever, right? So I'm going to say x plus 1, let's say the opposite of this is true, which is the same as -1 of that, is less than 7 before I do the flip. And if I want to undo that opposite, you could divide both sides by -1. And no, we won't do this step all the time. I just wanted to explain why it ends up working out. Dividing by -1, what do I need to do?
Flip the side.
Flip the inequality. And 7 divided by a negative, it changes that sign. So what I want to point out, normally we'll skip this step and we'll just go right over to here. And what we do is we flip the inequality and we change the sign of the right-hand side. Okay, so two things occur. Two things, right? So this changed and this changed. So definitely worth pointing that out. And you won't have to do, all of this every time, but this just explains why the inequality flips as well. So now I just solve both of these separately. Subtract 1, I get x is less than 6. Here I get subtract 1, I get x is greater than -8. And now I've got to figure out, is this an and or an or problem? Are these shaded towards or away from each other?
These are shading towards each other, so it's going to be an and problem.
Okay, we've got some claims here. Let's see, so there's 0, there's 6, there's -8. So notice how simple my number lines are. Let's see, less than 6 would be open circle here, shaded to the left. Greater than -8 would be open circle here, shaded to the right. So they are shaded towards one another. So this is graphically what it would look like. So sure, I could just put an and here based off of that conclusion, but the proper way to write this answer would be to write it as a compound inequality. And in order to do that, we write it from the least to the greatest. So the smallest of these things is the -8. The biggest of these things is the 6, right, on the graph as well. And the middlest of these things is the x, because x is less than the 6 and bigger than the 8, right, -8. So I'm going to put the x in the middle. So you can kind of see how my number line even makes sense, right? The 8, the -8, the +6, and then the solutions, the x goes in the middle. And since I have it written from least to greatest, I'll put all less than signs in between here. Haha.
I always feel like I'm gonna just forget the signs and do it wrong one day.
Yeah, so it does take some practice to be familiar with or make sure you remember the rules and all that. But yeah, so you have to write it as this compound inequality as a result there. So these will always be less than signs, unless like maybe this was closed and then they'd be like, could still have the equal part there. Something like that. But yeah, so as far as solving absolute value inequalities, this is the one change right here, is you flip it and change the sign, whereas previously we just changed the sign is what we used to do. So let's look at another example, shall we? Yeah. Methinks we shall. Let's see, I'll scroll over here and up here. Example.
That was nice.
Oh, thank you. Let's see, so let's paste this over here. Paste. Paste it like kindergarten. Here we are. So I've got this absolute value, inequality. What do you know? So I'm gonna break it up. And of course, if this absolute value wasn't isolated yet, if there was like a +1 or something on the outside, the first thing I'd have to do is move that, get the absolute value isolated. So it's got two situations. Either negative 2x minus 3 is less than or equal to 15, or negative 2x minus 3. Two things happen: flip the inequality and change the sign of the right-hand side. Right, so notice this and this changed, right? Two things. And now we just solve. Add 3, add 3. Hey, happens to be the same step over here. As long as I'm using my second color writing utensil, I might as well do that. Let's see, this is 18. This one would be negative 2x's. Do I have to flip the sign? I added 3 to both sides? No, no, perfectly legal move. Negative 15 and 3. Let's see, signs were different, so I get 12, and the more influential was negative. Ooh, you guys are good at this these days. Now what do I do?
You divide by -2, you have to flip the sign, so it's going to be x is greater than or equal to -9.
So let's see, dividing by a negative, all the same rules apply. Flip it. Yep. And over here, flip it. And, well, negative divided by negative is positive. So let's see, we've got to figure out, is this an and or an or problem?
It's going to be an or problem.
Let's see, greater than or equal to -9 would be closed circle. Greater than, shaded this way. And less than or equal to 6, shaded less than. So it actually does end up being an and problem. Color that in there. So how would I write this as a compound inequality?
-9 is greater than.
Less than or equal.
Why? Oh, okay. No, yes.
Because I'm technically kind of flipping this to write it in this order. To x, which is
less than or equal to 6.
yeah. And sometimes you might see your text write it this way. They might say it's the set. All right, this little curly brace means set of all x, and then this kind of single absolute value bar means such that. And then -9 is less than or equal to x is less than or equal to 6. So it's saying this: all of your answers are the following set of numbers. All right. So that's what this little part here means. The set of all x.
This is against the rules to sleep at lunch.
It is against the rules, yeah.
Is it really?
What do you mean? How could it be against the rules?
So that's what that notation means here. The set of all x such that this is true is what that means. So you might see that written there sometimes as well. All right.
That's what our homework looked like.
Yeah, they use the set notation at times, so that's why I definitely want you to be aware of it. Last example. Good stuff here. Example. Paste it.
Paste it.
Aha. What are you guys' thoughts on this one?
Should I waste one more piece of paper for this?
Use one more, sure.
Sorry.
It won't be a waste. It'll be
Okay,
worth it.
I think that you should add 5.
You guys agree? Why do you think he's doing that this time?
Because it's outside of the.
Yeah, it was outside the absolute value, so we got to get the abs val by itself before we break it up.
Now we can break it up.
Break it up like a Kit Kat. Here we go. Give me a break. Let's see. 3x is greater than 7, or 3x is less than negative 7. I agree.
Now divide by 3.
Do I have to flip it? Oh,
Nope,
but this one's negative.
That one, you have to-
doesn't matter, you're not dividing by a negative. You just have a
Ooh,
negative.
good argument. I'm dividing by a positive number, so I still don't have to flip it. So that's definitely worth pointing out there. So I've got x is greater than 7/3, or x is less than negative 7/3. So, and problem or problem?
And
Let's see, 7/3, by the way. 3 goes into 7 twice with a remainder of 1, so that's like 2 1/3. So if here's 2, here's 3. If here's 2, here's 3. Let's say. Negative 2's actually, and negative 3's over there. So let's see, greater than 7/3, it's 2 1/3, like I said. So it'd be an open circle shaded this way. And this one's a open circle shaded to the left. So they're shaded away. So it's going to be an OR problem. So I can actually, when I write my answer, I just throw a little OR right in between here. See that? Right here, just write OR, and then box it. And if I want to write that in all inside set notation, I could do that. So, yeah, my little rule of thumb, let's see if I can do this here. Hey, it's me. Hello. So I think of the shading, if it's pointing towards each other, right? Pointing towards, then it's an AND problem. If they're pointing away from each other, it's an OR problem, right? I just want to show you some pretty sweet, awesome, like, math hand gestures there, I guess. But it was worth it. It was worth it. So, so that's the idea. Thanks for watching, friends, and have a great day.